Hi, I'm Ajay Bardakjy.
And I'm Andrea Teran, and this is the creation of our glider Gliderang. So the project description, we just had to design, build, and test a balsa glider and document the experience. The requirements included a maximum size of 16 by 16 inches, primarily balsa wood, hand-thrown, no forms of propulsion or active remote control, remain intact during flight, and be stable enough to fly at least 20 feet. In order to succeed, we wanted to make sure that the size was less than 16 by 16, that we used the balsa wood materials that they offered, throw by hand without any external mechanism, and design stable body that flies at least 20 feet consistently. So for the building materials, we had balsa wood, which is lightweight and flies well, but it can be fragile, 3D printed parts that are sturdier but weigh a lot more, magnets or hex to weigh down the nose cone. Magnets can add weight in smaller increments but isn't as dense, so we might have to add more magnets. Hex nuts are denser, but the weight increments are much larger, so it's hard to fine-tune the weight we need. For wing shape, we consider swept back, which is more for transonic flights. Elliptical, which isn't very good for gliders because the uniform lift distribution can cause the entire wing to stall. And tapered is pretty good for stable flight and to increase the aspect ratio. And for dihedral, we had a slight dihedral, which is good because it provides lateral stability, and flat and anhedral don't provide very much lateral stability. So we chose the balsa wood with a 3D printed nose cone to weight it down. We used the magnets, and we also chose tapered for a stable flight, and a slight dihedral, which we created by bending the balsa after soaking it in water, and this provides a lateral stability. So for the size, we just wanted to maximize the wingspan and aspect ratio. So as you can see, the tape box is 16 by 16, so our plane fit inside it. And the center of mass can be seen by the little circle, but where we want it to be is the red X, so we used the nose cone to weigh it down.
So for our initial concept, we chose these set of parameters, but when we flew our glider for the first time, surprise, it did not fly. So through testing, we found that we had roll and yaw instability. Performance, our glider did fly 20 feet, but it barely flew 20 feet, and to be confident for a flight, we wanted to fly more. Here's a little video. So it did glide this second iteration. We did need to change the angle of attack. We felt that it was too strong, or too much at first, and then lift. So we actually had too little amount of lift from our wings. The surface area of our wings was not large enough to produce the lift required for the glider to actually glide. So with these changes, we added a larger vertical tail to create a larger moment for yaw and stability, added more mass to balance out the center of mass in regards to this neutral point, decreased the fixed angle of the wings so that we didn't stall the aircraft. We increased the surface area to increase lift, and then changed dihedral to flat wings because our dihedral was uneven, causing more problems than it was solving. So our final design looked like this: larger surface area for the wings, with still a small taper, but way less aggressive taper. The position of the wings is about the same, so that we could attach mass to the front of it to balance it out. And our angle attack is now 0 because we were getting too many stalling issues. So from this, we can calculate our aspect ratio and surface area. Aspect ratio came out to be about 5. Our center of mass, in the end, our center of mass was almost perfectly on top of the quarter chord of our aircraft, right where we want it to be for a balanced flight. So then we can calculate the lift and drag coefficients. I used 12 degrees of angle of attack that was what our best performance flight used. So our coefficient of lift was 1.313, and then calculate coefficient of drag. We had the profile drag plus the induced drag, which came out to 1.171, representing our airfoil as a cube for that coefficient of drag. So final checks. Our flight was good, or our glider was good to go for a flight day, flew around 65 feet, so we felt confident going in. But when we got to flight day, we had two 25-foot runs, and then our final run was 45 feet. So yes, it did meet the requirement of going 20 feet. It was a little bit unstable. We had some roll issues, which will be talked about in the next slide. But we did solve the problem of it gliding versus being thrown. In the first iteration, it looked like it was just being thrown versus the air actually carrying it further. So we did solve that problem. And then we decided to name our glider Gliderang because it had such roll to the right that it would actually, if you threw it hard enough, fly up and back around and straight at you. So areas to improve. Our center of mass wasn't perfect because we taped our magnets to the front of our aircraft. Every time it crashed into the ground, the magnet slid further back on the fuselage, eventually making it unstable and causing it to stall. Roll stability, due to a miscut, the taper was more aggressive on one side than it was the other, causing there to be more drag on one side, causing it to roll towards the right. Our angle of attack, more so on our throw, was too high, partially causing our stall. And then we possibly have too much lift now with the increased surface area of our wings, so we could, in the future, plan to, if we had more iterations, decrease the surface area by increasing the aspect ratio. And then here are our references. Thank you.